Hello and welcome to the channel Automotive Insights. In this lecture, I will cover the basic concepts of rolling resistance of tires. Rolling resistance is one of the most confused concepts in the automotive industry itself. Many secondary school students and undergraduate students or even graduate students also have similar difficulty in the proper understanding of rolling resistance. In this lecture, I am trying to bring more clarity on rolling resistance with the help of mechanics for both hard and soft surfaces. Now, let us come to the contents of the presentation. I am covering the rolling resistance for both hard surface as well as soft surface. I am covering the mechanics of rolling resistance first, then I will go to the free body diagram, then to the force equilibrium vector diagrams and the normal values of rolling resistance coefficients and an experimental setup and the relevant standards of ISO and SAE of rolling resistance and some out of box thoughts on rolling resistance and some more information on rolling resistance. Now we will come to the main body of the presentation. Imagine that a tire is rolling. As you can see in the picture, you all know that the rolling resistance is going to oppose the motion as shown in the picture. The rolling resistance is not due to friction. Yeah, I know that some of you are surprised by this, but we will see the reasons in the coming slides. The fundamental reason for the existence of rolling resistance is due to a class of material called viscoelastic material. And to understand more about how the rolling resistance is happening in a viscoelastic material, we need to recollect the concept of perfectly elastic material. Let's take a perfectly elastic material as you can see in this picture. So here we will take a material and we will fix on the base. We will apply a force on it and we will measure the corresponding displacement. Now we will plot the force and the corresponding displacement in this graph. Finally, we end up in a plot like this, and this we have achieved by increasing the force from 0 towards a maximum force, and we have a corresponding displacement related to that maximum force. In this experiment, we have loaded from 0 0, that means at 0 force 0 displacement, to a maximum force and maximum displacement. Then we unloaded the material. In this process, no energy is lost in a cycle of loading and unloading because the loading cycle and the unloading cycle they coincides and there is no area entrapped in between. Now let's do the same experiment for a viscoelastic material. Here what you can see is a viscoelastic material. We do the same experiment. That means we apply the force and we take the corresponding displacement. We plot the graph here and what we get is something like this. That means the loading curve, which is the top one, and the unloading curve are now different curves, and we achieved this by loading to the maximum point and unloading from there. As you can see, the red arrow is the loading curve and the green arrow is the unloading curve. An area is entrapped in between. You can see the shaded area, and energy is lost in a cycle of loading and unloading during the process, and this is due to the hysteresis of the material. We will see hysteresis in the next slide in more detail. So in this slide we will talk about hysteresis and tire normal stress. The fundamental reason of energy lost in a cycle of loading and unloading of a viscoelastic material is due to the property of hysteresis. As we have seen in the last slide, the area entrapped between the loading and unloading cycle is due to hysteresis. Rubber is a viscoelastic material and thus has hysteresis property. Now we will directly go to an application. Consider a tire. What you can see in the picture, the radius of the tire, also known as the geometric radius, is the distance from the center to the outermost point of the tire. So this notation here we follow is RG for geometric radius. Now keep the tire on the ground. Then what happens is Since rubber is a deformable material, it deforms and it's no more a point contact but an area contact between the tire and the ground. Due to this deformation, the radius Rg reduces to Rw, which is the loaded radius due to weight W. So Rg is greater than Rw, obviously. So at the contact patch, the tire is compressed and the normal force is distributed over a contact patch. So normal stress is acting at the tire interface. So as I have mentioned, the weight W is acting, that's why the tire is deflected and the Rg has reduced to Rw. Now there is a normal force acting on the tire and its magnitude is equal to W. So Fz should exactly match W in a static equilibrium condition. Now the Fz is the contribution of stresses starting from the one end of the contact patch to the other end of the contact patch. And stress distribution usually takes the form of a parabola. It's usually assumed as a parabola basically. And this is the popular form of assumption. You can even assume other forms of stress distribution other than parabola. So the stress distribution is normally approximated as a parabola. It is logical because at one end the stress is 0 and it is going to be a maximum at the center, and the other end it is again going to 0. So parabola matches this requirement, and this is why parabola is a good candidate for the stress distribution in a tire. Now we have come to the slide where we will discuss about the behavior of a tire on a hard surface. In the picture you can see that a tire is loaded by a weight W at the center and is acted upon by stress at the tire rod interface. All this stress sums up to form the force Fz. Now let me enlarge this stress plot here and put it below. This shows that any element we take here about the symmetrical axis of the tire and the corresponding element here, both will apply the same stress. If you take an element here and element here, they too will apply the same stress. This applies for all the elements, and thus the stress distribution is symmetrical about this vertical axis of the tire. Now we have plotted all the stresses. Then if we sum up all the stresses, then we are going to get the Fz. Completing the profile, we get the same parabola. Now we will see what happens when the tire rolls. Is the stress distribution going to be the same or is it going to be different? We will see now. Let us roll the tire towards right direction and take an element about the symmetrical axis on the right side of this tire, and on the left side take another symmetrical element corresponding to the red one you are seeing. So basically the red element and the green element are symmetrical elements about the tire symmetrical center line. Now let us redraw the graph for the viscoelastic material which plots force versus the displacement. Why this is valid here? Because each of the element is getting compressed when it enters the contact patch. It compresses to the maximum at the center and then it decompresses, and now it is free when it comes outside here. So every element is getting compressed and decompressed, that you will agree. Now let us see how each of the element are coming and fitting into this graph. See the red element, it is compressed by a quantity. As you can see in this picture, this is the compression amount, and the green element also has the same compression because we have assumed symmetrical elements from this symmetrical line. But what about force? The force on the compressing element is higher than the force on the decompressing element, and we scale it up the forces and drawn here, you can see that the force on the compressing element is higher and the force on the decompressing element is lesser. Now let us see what happens to the other symmetrical elements. So let's take another symmetrical element, maybe here, and draw the forces, and you can see that the same pattern follows. That means at the front side of the tire more force is exerted by that element, and on the rear side lesser force is exerted. The same thing is true for all other symmetrical elements. That means the front part of the tire will have more forces and the rear part of the tire will have lesser forces. Again, the same pattern follows. Now, if you take the resultant of all the stresses, we will end up with the force Fz, which is exactly equal to the W. But now you can see that this resultant is shifted by a displacement E, because the higher stresses are acting on the front side, so the resultant definitely has to come some distance towards front. Now let's complete the profile and we get a distorted parabola. In this slide we will see the action and reaction pair, and finally how the rolling resistance force is coming to existence. This is the same picture that you have seen in the last slide. So the weight is acting and the loaded radius is Rw. The normal force is acting at a distance E. In order to understand the effect of Fz acting at a distance E, we need to bring it to the same line of action of W. So if we do that, then we see that a moment is also introduced to the system. The quantity of that moment is Fz into E. That is the moment due to eccentricity. Now, in order to balance this moment, we need to have another force in the entire system. So that force is basically the rolling resistance. And if we shift this force Fr towards the center, then you can clearly understand this Mr is also acting in the system, which is the moment due to rolling resistance. Now you will agree that these both moments, which is created by the Fz acting at a distance E and the moment created by the Fr acting at a distance Rw, they are equivalent opposite and they are basically action and reaction pair. Since they are action and reaction pair, we can equate them. That means Fz into E equal to Fr into Rw. Now rearrange this equation and we get Fr in terms of E and Rw and Fz. Naming E by Rw as mu r, we can write Fr equal to mu r into Fz, where mu r is the coefficient of rolling resistance. This equation may resemble the normal friction equation that you know. The pattern is same. That means N is a normal force and F is a frictional force and mu is a coefficient. Here also the pattern is same. Fz is a normal force and Fr is the rolling resistance force, and whatever the coefficient coming here in this case is the coefficient of rolling resistance. It is important to note here that the mu r in some of the textbooks, especially in the undergraduate textbooks, they tell that E as the mu r, but in practical and in the automotive industry the mu r is basically E by Rw. That's what I'm following here. Now let's see the free body diagram of the wheel that we have discussed already. Now you know that the forces acting on this tire are the weight W, the normal force Fz, and the rolling resistance force Fr. Suppose this wheel is a non-driven wheel. In that case, we need to provide an additional force Fp in order to sustain the motion, and this Fp should be equal to Fr if you want to sustain a uniform velocity. Now let's see what happens in case of a driven wheel. For a driven wheel, everything same except instead of a force Fp, a push we are going to give at the center of the wheel. What we are going to do, we are going to give a torque at the center of the wheel, so that for that torque there is a reaction force Fp acting at the contact patch, which pushes the vehicle forward, or which sustains the vehicle to keep the velocity as constant. Note that this Fp should have a same magnitude as Fr in order to have the velocity as constant. Now let's come to the force equilibrium diagram for these both cases. Weight W is acting downwards. Now Fp in both cases you can see that it is towards right. Now the resultant is as shown here, and the normal force, keep it here, and Fr, let's keep it here. Then the equilibrium is achieved by summing these two, and this E is the equilibrant which balances the resultant. So basically this is the free body diagram for both a non-driven wheel as well as a driven wheel. This is interesting because even though these are two different cases, non-driven wheel and a driven wheel, but the force equilibrium diagram came in same. Now we have come to the second part of the presentation to deal with the tire on a soft surface. A good example of a tire on a soft surface would be an SUV going in a sand dune in a desert like this. So SUV peers into the sand and forms a profile like this, or a tractor going on a paddy field where the tractor tire and the mud is here, so mud is displaced and it forms like this. So you can imagine several situations having this kind of tire on a soft surface. Now let's see what are the forces acting on the tire. You can see that at the extreme end forces are 0. Now coming to the towards center, you can see that forces are getting increased. That means the distribution is approximately a parabola, as we have seen for the case of tire on a hard surface. But here note that we have not considered the shear stresses on the tire. That means only the normal stresses are considered, because it is important here to study about the effect of rolling resistance. So we do not give a torque to the system in order to have a shear stress at the surface. So that is the reason we do not have any shear stress here. Now this is the case of a tire when the tire is standing still, and all the stresses will combine to form Fz, the normal force. Now what happens when the tire rotates and moves? Still we can assume that there are no shear stresses at the contact area of the tire and the surface. As you have seen in the last case of the tire on a hard surface, and you have seen the viscoelastic property of the tire, the same way some kind of plasticity property is also present in the surface. So we can see that the front part of the surface will exert more force than the rear part. The same pattern continues. Now you can see that the resultant of all these stresses can be drawn as Fn, and this will pass through the center of the tire, because we have assumed the normal force. Each of the normal stresses should pass through the center of the tire, and thus the resultant also should pass through the center of the tire. Now this resultant is acting at a theta with respect to the vertical axis, and let's give a name E, at which the resultant is acting on the tire. Let's complete the profile by drawing this outer profile of this parabola like figure. Now let's split the normal force into the vertical and horizontal components. So Fz is the vertical component, and Fn, you know, it's acting at a angle theta with respect to the vertical, and Fr is the rolling resistance force. Now let's consider the geometry of the tire. I'm reproducing the same triangle here. So this vertical line is Rg and the angle is theta. Now considering the vertical equilibrium, we know that the only vertical force which is acting on this tire is W, and this should be reacted by a vertical force, and that vertical force is the force Fz. So Fz should be equal to W. Now let's establish a relation between the components of Fn, that is Fz and Fr. Fr equal to Fz into tan theta. This we can very well get from this diagram. Now geometrically from this picture you can see that tan theta equal to E by Rg, and replacing the tan theta here we get Fr equal to Fz into E by Rg. Now naming E by Rg as mu r, where mu r is a coefficient of rolling resistance, we can write Fr equal to mu r into Fz, and similar to the tire on a hard surface we got the similar result. So F equal to mu n is the normal friction equation we know, and this new equation is also resembling similar, so that's why we call this as coefficient of rolling resistance. Now let's come to the free body diagram of the wheel on soft surface just now we have discussed. So these are the forces acting, and this Fp should act in order to sustain this tire with a uniform velocity. Now let's see what happens in case of a driven wheel. In a driven wheel we know that we have to apply a torque T to create a force at the interface of the tire and the ground, and that force Fp should match the horizontal component of Fn. Now let's see the force equilibrium diagram of the both cases. Weight W is acting and Fp is acting on both cases, and resultant R is the resultant of Fp and W. Now we know that this Fn, or the normal force, is acting directly, and this is the equilibrium for this resultant, and this Fz is the vertical component of the Fn, and Fr is the horizontal component of Fn. This completes the force equilibrium diagram for both the cases. Again, this is interesting because we have only one force equilibrium diagram for a non-driven wheel and a driven wheel. Now let's come to a slide where we discuss about the normal values of coefficient of rolling resistance. This chart is taken from a book called Theory of Ground Vehicles by J.Y. Wong, published by John Wiley & Sons. This is a very good book for vehicle dynamics. From this book I have taken this table, and you can see that for a road surface of concrete, for a car tire, the rolling resistance coefficient is 0.013, and for a rolled gravel it's 0.02, and for different surfaces they have listed here. Now in order to see practically what this implies, so let's take an example. For a car tire rolling on a concrete and Fz equal to 1000 Newton, that means weight is acting at a magnitude of 1000 Newton, that's why we have Fz as 1000 Newton. Now the rolling resistance in this case would be 0.013 because it's concrete and it's car tire. So Putting directly into this equation, we get mu r, substitute this value, and Fz is 1000. We get Fr as 30 Newton. And note that for a normal force of Fz of 1000 Newton, the rolling resistance we get is just 30 Newton. This is very important to understand. So this is the visual illustration of what we have spoken just now. So weight is 1000 Newton and Fz is also 1000 Newton, and rolling resistance what we get is 13 Newton. Now one of the very important question to be asked is how to obtain mu r of a tire. Can the pressure distribution be measured and then we have E by Rw equal to mu r or E by Rg equal to mu r? This one, as you remember, in case of a tire on a hard surface, and this one, as you remember, in case of a tire on a soft surface. So it's not impossible to get this. We can get Rw is definitely measurable, Rg is also definitely measurable. What about E? E depends on the distribution of the stresses. So this is measurable by sophisticated equipments with high precision, but understand that this is not required because there are more easy methods to obtain mu r. And now we are going to see such an experimental method. See that two wheels are rolling and there is a strong belt which is running through the two wheels, and you can see that there are small rollers also in order to support the top part of the belt. An electric motor is running these wheels. You see that it's rotating in an anti-clockwise direction. Now in the top part the velocity is from right to left. As you can see the velocity direction here. Let's keep a wheel on the top of this strong belt with radius Rg, geometric radius. Now let the angular velocity of the wheel is omega. Let's load the tire by weight W, and you know that the normal force is going to act, which is the Fz, which will be equal to W. And obviously since the tire has this viscoelastic property, and what we have seen is that the rolling resistance force is going to act in the direction shown here. That means from right to left. Now let's support this tire and the weight by a structure which is attached to a rigid structure by a force transducer measuring device. What is the reason for having this force transducer device? Because this Fr which is appearing here can be measured here, because this is the only place where this Fr can be reacted. So this Fr is measured using the force transducer here. Now you have Fz, because Fz is basically W. Now rearrange the equation and we get mu r equal to Fr by Fz. Fr you get from here, Fz you get from here. Then divide and you get this coefficient mu r. So this is much easier compared to get E using precise instruments and substitute, and having the probability of errors are very high. So compared to that, this method is very easy and practical. There are few standards pertaining to this rolling resistance. These are ISO 18164 and ISO 28580 and SAE J1269 and SAE J2452. In some of these standards, you can see that the principle we have explained here is followed. In this slide, I will talk about a few remarks on the coefficient of rolling resistance. The same method of testing can be extended to the deformable surfaces. The last slide, we have seen that the test setup had this pulley and the strong belt, and if the strong belt is kept with some sand on the top, then this test is extended to a deformable surface also. Now, for a given tire, the rolling resistance coefficient values are different for different surfaces from hard to deformable. So you will agree that for a given tire, the mu r differs when it goes to different surfaces. So this is to understand that coefficient of rolling resistance is not only dependent on tire. Now for a given tire, lowest mu r is obtained for the hardest surface because hardest surface is more rigid and the deformation of that surface is much lesser, so lowest mu r is obtained. For a given tire, the higher the plasticity of surface, higher is the mu r. Higher the surface deforms, more energy we spent, and that is why we get more rolling resistance. For a tire rolling on a deformable surface, energy is spent to deform not only the tire but also the rolling surface. So this is important. Rolling resistance and the tire both are deformed. So one can conclude that mu r not only carries the property of the tire but also the property of the surface as well. This is very important because many people think that mu r is a constant for tire. No, it depends on different surfaces. That is why we have seen the table 2 slides back. That same table describes for a given tire how much is the rolling resistance coefficient on different surfaces. In this slide, I will talk about some of the out-of-box thoughts on mu r. The first and the most important question is it possible to make mu r as 0? Yes, in a hypothetical case with the following conditions. Tire should be rigid or perfectly elastic, and rolling surface should be rigid or perfectly elastic. You can see that there are 4 combinations we can have here: rigid tire and rigid surface, rigid tire and perfectly elastic surface. Same way, perfectly elastic tire and rigid surface, perfectly elastic tire and perfectly elastic surface. So if we have any one of these 4 combinations, then we can get mu r as 0. But unfortunately, both rigid and perfectly elastic are hypothetical. That means they do not exist in real world, only we can approximate them based on certain circumstances. In this slide, I will talk about some of the practical aspects of rolling resistance coefficient. In the last slide, we have seen that we cannot make the rolling resistance coefficient as 0, but now we can think of how to reduce the rolling resistance coefficient. Let us catch the tire first. We know that rubber is viscoelastic and we have to use rubber for most of the automotive applications as of today. Select a material with less viscoelastic property to reduce mu r. This is one valid suggestion. But for practical tire materials, usually there is a trade-off between hysteresis and traction. That means when you try to decrease the hysteresis, that means when you try to make the material as more elastic, then what is observed is that the traction property is also coming down. So the viscoelastic material or the rubber under consideration should have some hysteresis, or the material which is having this traction ability will have some hysteresis property attached in it. If you try to reduce the hysteresis, then the traction is going down. This is what is observed usually. Now coming to the ground, you have attacked tire. Now coming to ground. So ground, we do not have much control because it depends on where the vehicle has to travel. If the ground is concrete road or paved road, then it can be approximated as rigid. Then this is a good thing because rolling resistance is lesser for a concrete road or a paved road. In this slide, I will give hint on more on coefficient of rolling resistance. There are several factors which affects the rolling resistance coefficient like speed, inflation pressure, tire temperature, surface condition either wet or dry, then rubber compounds, construction of tire if it is radial or base ply, then effect of camber angle on the rolling resistance and effect of slip angle on rolling resistance. Then also, it is important to discuss the viscoelastic models of rubber, how the enclosed or entrapped area is coming between loading and unloading curve. All these things will be covered in the lecture Rolling Resistance of Tires Part 2 Advanced. Thanks for watching. If you like the content of this video, please like this and subscribe to this channel. I'm coming up with more interesting vehicle dynamics topics. Also, share it with someone who is an automotive enthusiast. Thank you. See you in my next video. Bye.